All right.
Are we
Good
good?
to go.
All right. So I'm JJ Christie. This is Megan. That guy with the wrinkled shirts of mine. We did our Bad Physics online flash game on Bowman 2, and it's made by the Free World Group.
The objective of this game is to shoot an opponent that's set at a fixed distance away from you. You have an arrow, you have to change the velocity and the angle to hit your target. The objective is to hit your target twice in order to win. And now I'm going to demonstrate the game.
And then the distance, it changes after each shot, so it kind of varies, makes it a little more challenging. The ad comes back on again.
Maybe I shouldn't click the link. There we go.
Okay, there we go.
See, there's different game modes. You can go against another human or the computer. You can practice. You can go bird hunting. Each game mode is different. I'm going to go against a separate human and succeed. You can click anywhere on the screen, and once you click and pull back, this number at the bottom is your velocity. The number at the top is your angle. You can change the angle by moving up and down with the mouse, and you change your velocity by moving back and forth. Here, in order to shoot, you just release. And there's my distance. Here, as you can see, I shot over the opponent because it went past it. And the best strategy for this game is basically trial and error. And since the distance changes, you have to figure out a new angle and new velocity for each game. That's a miss. So I'm going to try 45 or 38 at 71. Okay. Yeah, that's how the game works. So.
And then eventually, if you do land a shot, little graphic, little blood squirts out of the guy, as you can see in that picture right there. So that's how it's kind of played.
Alright, for our qualitative, we figured out that the flight time has to be the same as it rises and as it falls. That's projectile motion. So we figured out that according to chapter 4, the only thing that can be affected on the arrow is the gravity. And so that's the only thing, it's the Y component, not the X component. So we just did a few shots that were straight up. We had a velocity of about 10, which is V, and then we shot another one straight up at a 90-degree angle at 2V, which is 20. And we observed that the flight time was about twice the amount of time, which would say that physics is correct.
Okay, for our second qualitative, there's a setting you can go into in the game where it adds a wind. So normally in the game, it's just a straight shot with no wind. So your only force acting on the arrow is gravity. So the only acceleration on the arrow should be in the Y direction. So the X direction velocity should be constant after you shoot. But so there's a setting where the tailwind was added. And we observed the shot without the tailwind, in fact, did travel at a constant speed. And then once the tailwind was added, the wind did accelerate the arrow. You shot the arrow and you could see it speed up with the wind behind the arrow. So with an added force now in the X direction, we should see an acceleration in the X direction. And this is Newton's second law, which is an object's acceleration is equal to its net force divided by its mass. So since the arrow has some mass, which is not really important, when there is a force added in the X direction, which would be the wind, it should have an acceleration. And we did, in fact, see that. So this did agree with the law of physics. It took it into account in this situation.
For our quantitative, we tested the flight time that we had, and like I said, it was dependent on the Y component. So we set up 2 different trials to see what the time would be as soon as it was shot to when it landed. So for this thing, we assumed that the mass and the gravity was consistent throughout the entire game. So with that said, F equals ma, we can assume that since the mass and the acceleration are the same, that the force would be the same, and that's according to Newton's second law. So using a kinematic equation, Vf equals Vi plus the acceleration and the difference of time, we rearranged it to solve for the change of time. And the Vi is always 0 because because it's staying at rest in his bow and arrow. And so for the first trial, we kept the angle the same to be around 30, but we ended up having 29.88. That's just how the game came to be. Our first velocity was 43. We didn't have a unit, but we assumed that it was meters per second. And when we shot it, we had 1.03 seconds. So when we doubled the velocity on the second trial, keeping the angle the same, we had the time be 2.07 seconds.
So then when you double the velocity, it flies farther, so then it should stay in the air for twice as long. Exactly, if it followed real world measurements. So we found that, in fact, it pretty well matched what we would think we'd find in the real world. Specifically, again, as we've been talking about pretty much this entire time, Newton's second law, and also the concept of flight time, that t rise and t fall is equal to the total flight time. So, as I said, in real life, the time should be twice as long with the arrow flying twice as fast. So that is in the y direction, of course. So we use a percent difference equation, our measure 1 minus our measure 2, divided by the average. And we found our percent difference to be about 0.5%. So that's pretty close. In cases of any of the experiments we've done here, we found that if we're within about 5%, we're fairly accurate and we can say that that's true. And so for this, 0.5% was a great value. And sources of error, to maybe some reasons why we weren't exactly on the dot, that 0% difference, is the stopwatch wasn't expanded maybe to enough decimal places to get the exact time of the flight. As we said before, the angles. As I said, it did really follow the laws of physics very well.
In conclusion, this game did follow the laws of physics. More importantly, Newton's second law. We agree with the fact that the game would be very difficult if it didn't take into account physics. There would be no force of gravity causing the arrow to take on a parabolic trajectory. It would just float in the air. And also, physics mattered heavily in this game. It was very important. The game was needed. Thank you for listening.
I would say, just to add to that, I would say, what would be the point? Like Lamont said, the arrow would simply float. There'd be no way for you to judge, how you would need to adjust it if it didn't follow some sort of physics, and there was a constant acceleration. We don't necessarily know if it was gravity, but the game is pretty much physics. If there's no physics involved, the game really has no point.
Also has no reward of seeing blood and gore.
So that's our
presentation. Thank you for listening.
All right, let's thank our speakers. Questions?
Okay, didn't you say that the time from when it left to when the times are supposed to be equal in the two halves of the parabola?
right.
Did you not take into account the height of the person then? Because doesn't it go from the person to the ground?
Well, it doesn't. Since it shoots from the same spot. If we take the spot that it shoots from, the height of wherever it is, it's not really the height of the person doesn't matter because it's always the same. So if we shoot it and then once it gets to the top, we shot it straight up, so it comes down and actually hits the person. So it kills yourself, I guess, when you're shooting, but it takes into account the person. So it doesn't actually hit the ground, it hits the person.
Oh, okay.
Does that make any sense? So if I'm like shooting an arrow, I shoot it straight up from about my head, then I let it fall. So if we measured when the arrow turns around, that time right there, to when the time it hits me in the head, it's the same on each half.
Okay. So release it from the same distance and hitting and landing at the same distance.
Another question? All right, I'll ask my question. Were you surprised at how accurate it was, or precise? Which one is it? Great question. Are you surprised at that low percent error?
Actually, yes, because
Yeah.
we would have
Yeah.
thought that the gravity or the mass of the arrow would actually be different throughout the game. We didn't think that it would be this consistent.
Okay. Cool. All right, let's thank our speakers again.